Now, it's cute to have a series which changes its sign, plus and minus, every single number on my list, right? A positive, then a negative, then another positive, then another negative, and so on. But that's not always going to happen, right? There are plenty of other lists of numbers where sometimes the numbers will be positive, sometimes the numbers will be negative, but they don't come in such a neat pattern. How can we talk about their convergence then, if they're not an alternating series, but they still have some negative numbers on that list? So if I have any series, any one at all, where I'm trying to add up an infinite list of numbers, starting at A1, and then A2, A3, and so on, maybe some of those numbers are positive, maybe some of them are negative, but no matter what, they will all have some absolute value. So I can build a new series where instead of adding up the numbers an, I add up the absolute values of the numbers an. So this gives me a new series, and one that we'd be able to treat with our convergence tests from the past couple lectures. So if I know that the sum of the absolute values here converges, I'm going to call that original series absolutely convergent. Right? So I have a series. Its entries may be positive, maybe negative. Maybe they come in some nice pattern, or maybe they don't. If I take the absolute values here, I get a nice series whose numbers on the list are all at least 0, so 0 or positive. If that converges, then I'll say the original series is absolutely convergent. So absolute convergence is going to mean exactly the same thing for a series that was already positive to begin with. And I can look at, say, an alternating series. Here I've got the summation n from 1 to infinity. My sum ends have the formula -1 to the power n minus 1, all on n squared. So I'm looking at 1 minus a quarter plus a ninth minus a 16th and so on. And I ask, is this absolutely convergent? Well, yes, it is, because when I take my absolute values here, I get just a regular p series, p equals 2, and so that converges. So here's an example of absolute convergence. I can try that for the harmonic series, right? So here's my alternating harmonic series, 1 minus a half plus a third minus a quarter and so on. And that again, well, if I take absolute values here, this diverges, right? This is the ordinary harmonic series after I take absolute values. So this is not absolutely convergent. So why do I care about this? And that's the reason is this theorem, number 3 here. If the series, the summation of numbers a sub n, is absolutely convergent, then it will be regular convergent too. So this limit will exist so long as take absolute values and I still have something that converges. Now, some series will converge, but the summation of the absolute values diverges. So we'd call something like that conditionally convergent. And an example of it is right here. The alternating harmonic series converges by the alternating series test from my previous clip, but the absolute values of those numbers, when I add them all up, diverges. So absolute convergence gives us convergence, but some series can only converge because they have those minus signs in them. We call those conditionally convergent.